the process that we used earlier of using Excel to generate the 2 and 3 letter combinations, was that efficient? Combinations आपने generate कर लिए. I think the bigger question is how would you validate them? And there were a lot of combinations. So first round आपके पास 42 आए थे, and then those 42 into 7, ignoring replacement would be 42 into 5 is say 210. And then दो और, तो about almost about 300 combinations. फिर 4, फिर 5, फिर 6, फिर 7, फिर 8. So if you sort of keep on going through the process, the process is very tedious, right? So that doesn't work. But what is the process that we followed? What is the sequence that we followed when we were generating these combinations? And we were coming up with the right words, the right choices that we needed to use. To generate the possible letter combinations, then filter for valid words, then validate words, and then store the words, right? And then match those words against a dictionary where you had a list that you could compare that. Two challenges. One is this whole filter, validate word challenge. How can we do this faster? And then the second challenge is the dictionary search challenge. How can we do this faster? So these are two questions that we'll come back to multiple times in this course. From an assessment perspective, there is a variety of ways to test for this. So, obviously I can give you a tile and ask you to come up with words and ask you to come up with 3 or 4 letter words, but then ask you to come up with not just the most, the full list of words, but also a combination of words, right? So, Sawalat perspective say, when I share the deck, I've already shared this version for Thursday. You'll now have a copy for the Friday conversation. When I share the deck, take a look at these questions and see how would you attack them. So, agla sawal, the next big question that comes up is, if you are building a game AI and the objective of that game AI is to play Scrabble, what are the components that that game AI should have? So, remember we go back to our analysis design framework, we go back to our actor role behavior framework. What are the different components that engine that can play Scrabble with you should have? So one part of it is obviously word generation, word validation, and dictionary search. One is how do you place those words? One is what is the relevant strategy that you should use in the game when you move forward with the game. When you look at a Scrabble board, is there a way for you to assess? Is there a way for you to tell whether one player is more likely or less likely to win or lose the game? Is there a way that we can calculate the probability of winning and losing given the status of the board? So here, for example, I've got 4 different components that I'm interested in that I want to use to figure out and evaluate how do I calculate those probabilities. The components are, the first component is stage. What is the stage of the game? Where are we in the game? And for us, I think stage is essentially determined or evaluated by the tiles on the board or the tiles remaining in the bag. Second component is leverage. If you're a skilled player and you can take a shot at the special squares, these triple word scores, a bingo with a triple word tile on any of the special squares can completely change the dynamics of the game. So you might be losing, but you may actually end up winning with one last big play. That is a function of your skill. It's also a function to some extent of your luck, but ultimately it's a function of how can you take what the board offers you. So we use, in the model that we're working with, we use the number of these tiles remaining to get a sense of what can you do on the leverage front. Then the third piece is a differential between the two players. So in this case, wrist trainer, that's me, and my score is 255. Zoe is the computer. Zoe scores 254. The differential is just a single point. And then the last element is luck. Which ones of the highest scoring tiles are left? So for example, Z is 10 points, Q is 10 points, X is 8 points. How many of these high scoring tiles are left? And the reason why I say we link this to luck is because when the tile bag gives you a tile that does that on a randomly generated basis. Question board evaluation is trying to address and answer is that if I put all of these components together, for example, in this case, you'll see that the stage of the game is -100. So the game is done. We've played the game. The game is over. Leverage wise, there's about a 46% chance that the player might be able to, if the game was going on, there's a 46% chance because 1, 2, 3, 4 of the tiles are still left. Differential wise, there's not too much of a difference between the two players. It's just 1 and 1. So, the difference is between 255 and 254 is 1. Luck wise, only one tile is left, and that tile is Q, and Q, as we know, scores about 10. So on this basis, if you look at the board evaluation score, player 1 score is 34, minus 34.83. Player 2 score is minus 36.83, right? So 2 point ka fark hai. Who is winning? From a probability perspective, who has the higher chance of winning? If you ignore everything else on the board, if you assume the game's still going on, who is winning the game or who has won the game? 1 or 2? Player 1 or 2? Ignoring the scores you see here, right? Only looking at this part. Does the board evaluation give you a sense of which player has won the game and which player has lost the game? Player 1 is winning, right? So that from that perspective, board eval works. The reason why board evaluation is such an important key core concept is that think about what it does. It takes the entire board, takes the status of the entire board, wherever you are on that board, it takes that status. It takes the status of the tile bag, takes the status of the game, takes the status of how skillful or strong players the two players were, and it compresses all of that into a single score, right? Which is what? Which is minus 34.83. It takes all of this information, and compresses it into a single score. So a lot of time within the field of computer science, the challenge that we face is that we need to convey information, but we want to convey that information using the least amount of signals possible. And what we're really doing in this specific case with the board eval engine is trying to figure out what is the right signal that we want to use. The reason why I want to use this is because our take is a good board evaluation engine should be able to satisfy the right boundary conditions. So for example, at the end, it should be clear who has won the game. So we know this works. But what should be the score at the start? When no move has been played by either of the player, what should be the probability of winning and losing between player 1 and player 2? It should be 50-50. That's right. It should be 50-50. Very good. Then there is transition effectiveness, right? When you play a good move or a strong move and the score changes, do the probabilities reflect that change? Then should generate a signal that captures the essence of the most relevant information on the board. For us, that metric is probability of winning. What are we tracking? We're tracking the probability of winning, the stage of the game, the leverage remaining in the game, and the element of luck in the game. Before the first move is played, before the tiles are drawn, before anything happens, at that point in time, what is the probability of winning and losing? So one way of doing this is to play tic-tac-toe, right? So tic-tac-toe, that's my first move. Ab aap bataएं, what's the move that you'd like to play? Kya khelenge? Center, opposite corner, center, center, center. Okay, let's play the center. Very good. Let's play the center. Okay, now next move. Can you still win the game or are you lost? What is the probability of winning at this point in time in the game? Okay, so Rahim says bottom center. There we go. And now, can you draw it now, Rahim? Rahim says top center. Yeah, there we go. Perfect. So now Rahim can win, right? So now, if you think in terms of the flow and the structure of the game, what just happened? You had a winnable game and I lost it. How did I lose it? because I played the wrong move. But at this point in time, right, if you go back to one step, when we only had this move and this move, at this point in time, the game was wide open. Rather than playing this move, I'd played this move, then Rahim would have gone out and played this part and the game would have drawn. Okay, because then I would have done this part and then Rahim would have done this part and then I would have done this part and that's it, the game would have drawn. At any given point in time, even in a game like tic-tac-toe, which is a fairly simple game, there are multiple possibilities that you can predict and forecast. So at the start of the game, when we started, right, what are the possible moves? In fact, take one step forward, right? At this point in time, what are the possible moves? How many possible moves are there? Before a single move is played, before I played the X, right? So this is one move, this is two moves, this is 3, 4, 5, 6, 7, 8. There are about 9 valid moves. Each of these moves represents one possible future. So once I lock the move and play the move, then I think we are in a good shape. But for example, let's say if I picked one move out of these, and let's say that move was this one, right? Let's say I picked up this move. So at this point in time, what are the valid responses that my opponent has? The response that we picked was this one. So when you pick kiya, so what did the tree look like? What are you doing? You're projecting the moves stage by stage, level by level. So move 0, move 1, move 2, and move 3. At this point in time, there are 9 possible paths. Then for each 9 possible paths, there are 8 possible combinations. Then for each of these 8 possible combinations, there are 7 possible future moves. This is tree search. So the idea is to project where the game is going, to project the probability of winning and losing, and then to bring it back at this point in time to figure out what the right move should be. For us, within the context that we're playing, right? So if you've seen AlphaGo, the movie, AlphaGo has this concept of a value network. A value network basically evaluates what are the possible, probable, valid moves that you can play in a game. And within all of those probabilities, which is the move that has the highest probability of winning? So 50.48 is the highest probability of winning, and this is the move that the game would play. In Kara's case, what was the move with the highest possibilities? It was this, 0, and then this one, right? This was the move with the highest probability. If I had played this, I would have blocked the game and we would have drawn the game. But because I played this, what happened? Naeem was able to move in for the kill. The objective of tree search is to basically project the game in the future and see where the winning move is, and then to bring that move back. And it does that in AlphaGo, the movie, as well as any other game engine. It does that by doing 3 things. The first is what we call policy. What is a valid move? Second is what we call value search. What is the probability of winning for each of those moves? And how do you get this value search? We do this value search with the usage of tree search. Tree search is essentially projecting the game into the future, whether you're playing chess, whether you're playing Go, whether you're playing tic-tac-toe, or whether you're playing Scrabble, and trying to get a sense of where the winning moves lie. So for example, in this specific instance, right, which of these trees, which of these paths have the highest scoring words? So if you look at ahead, for example, right, so A is 1, H is 4, 1, 1, and 2. That's 6. So this adds up for a total of 9. What about trade? T is 1, R is 1, A is 1, D is 2, E is 1. So that's 4 and 2, 6. Bold, B is 3, D is 2, 5, 6, 7. This is 7. Zips, Z is 10, 1, 3, and 1. So 13, 14, 15. Which of these move has the highest score? So it's obviously, clearly, the answer is zip, which means that the path that you want should allow you to come here. And there are many ways, right? You can come from this side, you can come from this side, you can come from this side. There are many multiple paths that you can follow to get to the desired end state. But you should be able to predict and forecast what the desired end state is. If you can do that, then you can bring that back. So essentially what you're doing in the game of Scrabble with this probability of winning, P of winning, you're basically saying, I have these 42 possible moves, the 42 possible combinations. Which one of these is the winning move? Which one of these has the higher probability of winning? And if I get there and I get to the next stage, then what's the next move? So let's say the next winning move is here. So this is the path that I should follow. Do you now understand the reason why we have to calculate probability of winning? The reason why board evaluation is such an important component of building a game AI engine for playing Scrabble? Because P of winning compresses the outlook of the game into one single number. You don't have to worry about how many tiles are remaining. You don't have to worry about what the score is. You don't have to worry about what the outlook of the game is. You don't have to worry about the skill set of the players. You don't have to worry about the factor of luck. You simply say, compress all of that information into one single number and send that number out into the future so that we can find out where the highest number is. And once we know where that highest number is, then come back and tell me that this is the right door. Open this door and we'll get to the right path, which will take us to the highest scoring word. I've gotten a detailed description. I'll share these slides with you. They should be able to give you a sense of how I've put together the model. You've got some validation values here. So you've got both scores. So for example, in this specific instance, there's a score for player 1 and there's a score for player 2 based on the profile of the board and where we are at this specific point in time. Take a look at this. This is what the Excel model looks like. I'm not going to share the model with you. You'll actually have to build it yourself. So treat this as a pre-work, as an assignment of sorts that you should follow, that you should do to build the model in Excel. The assessment will have board evaluation questions in it, which means that you should have this model working. Even if a friend of yours builds this model for you, make sure that the model you have is something that you understand, that you can tweak and work with on your own by yourself. Because when the assessment is going on, nobody would have time to talk to you or tell you or explain to you how the model works. Ideally, build the model yourself. So I've now given you a full snapshot of what the different values look like. You'll have to figure out how to put them together and make them work together. The few things you have to figure out are explained here. This is where it describes what you're supposed to do and how certain numbers are calculated and put together. So follow the instructions, build the model. Once you build the model, test the model, calibrate the model. If the model works, if your values are right, then your answers will be right. If the model doesn't work and your values are not right, test the model. Think of this as a very simple assignment. This is the specification. So look at the specification, build the Excel model, test the Excel model, run through a couple of test cases, and see what the scores look like in your model and in the model that I have here. How do we present this information, right? So one way of presenting the information is to show you how the model works, how I've done the calculations, I've given you a write-up, I've given you an explanation. But an alternate way of presenting information is through what we call representation. We've already spent a lot of time on representation in our first class. Here's a different look. This is a truth table, right? This truth table shows you two possible views of the world. They may be true, they may be false. In this specific case, they are true. So for example, stage of the game. What does the stage of the game represent? It represents time remaining. Does it have a big impact or a huge impact on your score? It has a small impact on your score. Luck. Luck represents chance and opportunity, something that you don't control. Because you don't control it, it's not impacted by your skill. Leverage. Leverage looks at the player's skill. It sort of evaluates and maximizes the player's skill. If you have access to the triple letter word or double letter word tiles and you're a good player, you should be able to put that to work. Leverage can also change the game's direction. Differential, the score differential, matters the most in the final score and it determines who is winning. This truth table will only be true if all four elements of A or B are true. If even one of these is not true, then the truth table, representation within that table is not true. This is the second truth table, right? Stage, for example, what is the maximum value, the minimum value of stage? What is the maximum value of stage? What about luck? What about leverage? What about differential? So a truth table is one way of presenting and sharing information. Let's assume that you build the model, आपने तैयार कर लिया, and it's ready. and you're trying to figure out, okay, how do I calculate the values? How do I test the values? Well, here's a sheet. Gives you score at the start, score at the middle of the game, score at the end of the game. Does your model produce the same values? If it does, then you've calibrated it. If it doesn't, then your model is not right. It's not working properly. Here's the second variation, right? In this specific instance, score at the start, score at the middle, winning score at end game, losing score at end game. So if you think in terms of the structure of how information was shared, what did I share? First, I shared a spec. I said, this is how the model works. This is the structure of the model, right? This is part of the spec. And I've given you some test values to work with that look at the values that you see here. I gave you a list of drivers that are used in building them. After that point in time, what do? I give you a write-up that explains how differential, luck, and the calculation of differential and luck work. Then I give you how open is the board, talk to you about leverage. Then I give you a full screenshot and the linkages between how certain values are calculated, how they're put together. Then what do? Then I give you a different view, a different lens of what these factors represent. And then I give you 2 specific test cases that you can use to test the results that you've generated using the model that you've built. Okay.